Welcome friends, welcome to the Friday Colloquium. This week we have Eung Jin Chun from TIAS. Eung Jin did his PhD in string cosmology with the famous Jimmy King, and then after postdocs at Munich and ICTP, he went back to Korea, and now he's a full prof. It's been a full prof for several years actually. No, not now. Okay, for several years at TIAS.
Yeah, since 2002.
Since 2002. Okay. So almost 20 years he has been a full prof at TIAS. And today he's going to talk about what to do after the discovery of the Higgs boson. Over to you.
Okay, thank you very much. Yeah, in fact, I am very honored to be here and present a colloquium talk. Actually, I love this campus very much, also staying in the guest house. So I enjoy walking, although I cannot walk properly due to some injury, and also swimming in the beautiful pool. Okay, so as a colloquium talk, I decided to talk about a bit of discovery Higgs particle, and then some new trend of particle physics. So let's go back to the year of 1964 to start. So in this year, there appears series of papers written by 3 different groups. So all the work done independently, and then they realized that if there is spontaneous symmetry breaking of gauge theory, then there appear massive vector fields, gauge fields. Also, the massless Goldstone boson disappears. So this is a copy of one of the Higgs paper, and then here he wrote. He introduced one complex field, and then this phi 1 is massless degrees of freedom around the circling around the vacuum state, and then phi 2 gas of wave, non-zero wave. Then there is a radial fluctuation which becomes massive. So that is equation 2, and then this is so-called Higgs boson, right? It's a massive Goldstone boson, and then vector boson actually combined with the Goldstone mode, then it becomes massive. So this equation describes what we know now as a Higgs mechanism, or generally EBHGHK mechanism. But usually, to make it short, we call it the Higgs mechanism or Higgs boson. Since this equation for massive boson field appears in the Higgs paper first, so it can be justified that we can call it only Higgs boson. And then one interesting story was that the second paper of Higgs was submitted to some journal, and then it was rejected, being that it may be of no obvious relevance to physics. It's a purely theoretical argument why massless Goldstone boson could disappear. Also, vector gauge boson can be massive. But as you know, it has really huge impact in physics. So of course, around that time, we knew about the weak interaction, and then this weak interaction theory was first written by Fermi, right? Of course, Fermi didn't know about gauge theory. So at that time, he realized that if he write down these 4 Fermi interactions between neutron, proton, and neutrino and electron, so you can describe so-called beta decay of neutron going to proton and emitting 1 electron. Then obviously, there must be an additional field, neutral field, escaping the detector, which was, of course, introduced by Pauli for the first time. So his theory was able to describe all the nuclear phenomena, beta decay, inverse beta decay, whatsoever, very nicely. And also he could determine the size of the coupling which is now called Fermi constant. Now, this theory was developed to so-called SU2 cross U1 gauge theory. In this theory, of course, all interactions should be mediated by gauge bosons. So inside this small dot, there must be a virtual exchange of so-called W gauge boson, which is massive. And then integrating out this, we will be able to get this effective 4 Fermi interaction. And then this Fermi constant can be written in terms of Higgs vacuum exclusion value, which is 174 GeV, as we know now. So, so in this setup, I mean, the standard model was written. Basically, Weinberg wrote down the standard model completely. And then when actually Fermi introduced this theory, I mean, it's interesting to see the title of these two seminal papers. So tentative theory of beta decay, the model of leptons, very modest name. And then also right after this paper, I mean, Hans Bethe and Pyrrhus wrote a Nature paper saying that, okay, so this cross-section is too small to be observed in nature. But it was not the case. I mean, we now detect a lot of neutrinos in huge detectors, so there has been a lot of progress in this field. So now we know that the standard model consists of 4 gauge fields. I mean, electromagnetic field interaction mediated by photon, strong interaction mediated by gluon, and weak interaction mediated by G and W boson, which are massive. So this becomes massive due to the so-called Higgs mechanism, right? And then 3 copies of quarks and leptons. So first generation UDE, of course, consists all the matters in the universe. And then Higgs must be SU2 doublet. And then the neutral part get a non-trivial wave. So now, I mean, because of this original work, actually, these people got Sakurai Prize in 2010, and then 2 years later, Higgs boson was discovered at the LHC, and then these 2 people got Nobel Prize in the next year, 2013. Fortunately, the Englert-Brout was there in 2010, but Brout passed away, I think, in the next year. So he was not able to get Nobel Prize. So I mean, so here, I mean, the Nobel committee quote that this prize was for the theoretical discovery of the mechanism, not the Higgs boson. So I mean, yeah, provided that's a politically right statement. Okay, so actually there's another interesting story about Higgs, the name of Higgs boson. Actually, Benjamin Lee was blamed to give this name. So he was, he is a Korean. And then at that time, I mean, he was one of the leading physicists. And then he was giving a lot of lectures on gauge theory, smooth symmetry breaking, and numerability, and so on and so forth. So it was commonly accepted since 1972, when he gave a lecture on all this physics behind. He called this mechanism as a Higgs mechanism, and then also called it Higgs boson. So the name of Higgs boson was fixed since that time. So he also collaborated with Steven Weinberg. Of course, he got Nobel Prize due to his paper together with the Glashow and Weinberg, Salam, Glashow, about the establishment of a standard model. So actually, yeah, his contribution at that time was really critical in the development of this kind of smooth symmetry breaking and gauge theory, and so on and so forth. Okay, now LHC. So it's when it started, it started 2009 or 10, and then soon after, I mean, actually, the LHC was able to rediscover all the standard model particles. And then the final discovery of the standard model particle was G gauge boson, 1983. So also LHC rediscovered in 2010. And then next year, 2011 December, actually there was a 3 sigma hint for a new particle. So this is 3 sigma peak at around 120 GeV, right? So then everybody believed that, oh, that must be Higgs boson. So that was discovered by the reconstructing of 2 photons. So measuring the total energy of 2 photons, we get 125 GeV mass of new particle, which must be the Higgs. Then obviously next year, okay, these 2 experiments at the LHC was able to claim the 3 sigma, 5 sigma discovery of this boson. Of course, this event was, this announcement was held by some conference hall in at CERN, and then actually it was broadcasted worldwide. So this is the photo we are also watching this broadcast. So at the end of this announcement, everybody was really cheerful, and then Higgs himself was weeping. Okay, so by the end of 2012, actually a lot of data accumulated. Then there was no going back. No, it was not just a statistical fluctuation. So as data accumulated, the signal became clearer and clearer. So there were, a clear peak at 125 GeV. So here or here. So it fit with nicely the standard model description of Higgs boson of 125 GeV mass. So of course then, this event was celebrated by many worldwide, by many journals, and also original paper published in PLB, and then that was really a great event. But we were not able to enjoy this event very much. Actually, before the Higgs discovery, we was worried about this kind of happening. So actually, Alice also mentioned this in 2007. Earlier, much earlier, the discovery of the Higgs boson. He says that it would be really a disaster if only Higgs is discovered at the LHC, nothing else. So instead of discovering Higgs only, maybe discovering nothing would be much better for the future of physics, or maybe not. So then actually, LHC discovered Higgs, and then actually so far no new physics signal was discovered. Actually, after Higgs discovery, what people mostly anticipated was to discover supersymmetry particles. So the reason why that was anticipated will be the next topic. Okay, so standard model was completely finalized by the Higgs discovery, and then there were a lot of ideas about new physics beyond the standard model. Standard model was not really satisfactory. So there will be unification of 3 different forces: weak interaction, electromagnetic interaction, and strong interaction. Maybe there is some unified gauge group at very high scale. And then also we also realized that neutrinos are very, very light. It's massive. It's not massless. And then if you compare the top quark mass to neutrino mass, this is a huge hierarchy. So there must be some reason behind this huge hierarchy. So and then also there may be some high scale physics above the standard model NA scale, which is around 100 GeV. In the meantime, the prediction of standard model was proved more accurately. So top quark WG boson mass and B quark tau, and even muon coupling was measured precisely. So for this, we can come back to the Einstein's dream. I mean, he tried to unify gravity plus and then electromagnetism. So after writing his general relativity, I mean, people realize that if we do general relativity in 5 dimensions, so there is the 4-dimensional space-time metric which describes gravity, and then there is a 4-dimensional vector, mu5 component. So this can be the candidate of electromagnetic potential. So he was trying to complete the theory to describe electromagnetism correctly. So I mean, I also learned that so until 1953, starting from 1920, I mean, he tried to complete the theory. So it was really great effort, but at the end of the day, nothing came out. No success was made. And then, of course, during this period, actually, quantum mechanics developed to quantum field theory. So a lot of progress was made, but Einstein was trying to complete his unified theory in vain. And then, as you know, I mean, Einstein was a bit reluctant to accept quantum mechanics, which was kind of new physics at that time. Okay, so then during in 1970s, actually people realized that the 3 gauge forces could be unified in 1 gauge group like SU5, SO10, and then it can be even extended further up to E8 cross E8 and SO32, which was predicted, which was necessary to complete, say, sports string theory. So I mean, to have this, so supersymmetry was required for consistent string theory in 10 dimensions. And then the whole story may go like this. Okay, so we have 10-dimensional sports string theory having supersymmetry and gradient unification, and then the 10 dimension can be compactified to 4 dimensions. Then at the end of the day, we'll get to, I mean, this gradient unification group may broken down to the smaller group, and then finally our standard model gauge group. So this is the idea. But you know, I mean, the string theory written in around Planck scale, gradient unification theory written around 10 to 16 GeV. So yeah, basically, other than the theoretical architecture, maybe it's really impossible to detect. I mean, observe this kind of gradient unification group. But there was one hope that if there is a heavy gauge boson of SU5, SO10, then it can mediate, it can induce the proton decay. So this X can carry both quark and lepton number, so that through the virtual exchange of this heavy particle, proton can decay to electron and pion. So then people would really try to find this proton decay, which if you see the proton decay, then we can prove this is a proof for the presence of gradient unification indeed. So how do we discover this proton decay? So we just collect a lot of matter inside a big tank, water tank, and then this is probably now 50 kiloton of water. Then you can calculate how many protons are there. Then once in a while, one proton may decay to positron, and then we can see this positron, right? So now this is, you know, the Kamiokande experiment. I mean, that was why Kamiokande was started. And then now, so far we didn't see any signal like this. So the proton lifetime should be larger than 10 to 34 years. So in the future, maybe, yeah, so sensitivity limit is 10 to 35 years. So we may be able to see this proton decay in the future, but so far, no evidence for it. Okay, so now actually the era of supersymmetry actually started in around early 1990. when people realize that, I mean, in order to get grand unification, consistent, consistent framework, I mean, this is 3-gauge coupling, the strong gauge coupling, weak gauge coupling, and the electromagnetic gauge coupling should meet at one point at the unification scale, which is believed to 10 to 16 GeV. So then, if we introduce supersymmetry, so to have supersymmetry, I mean, for each fermion field, quark and leptons, we have a scalar partner, quark and leptons. For each for the Higgs, okay, the scalar, and then there must be a fermion counterpart. Also, spin 1 gauge boson should have its partner, which is also a fermion, which are fermions. So this is the consequence of supersymmetry, but then supersymmetry somehow has to be broken so that the super partners should have different masses. So then if you assume this, so super partner masses should be around 100 GeV or TeV around the electroweak scale to have, so I mean, if they are too light, we should be able to find them. If they are too heavy, I mean, having these guys around the TeV scale, so we can explain the origin of Higgs wave scale, which is about 100 GeV. So that was one of the main motivation. And then the other motivation is that, I mean, around this time, the 3-gauge coupling constant was were measured precisely, and then extrapolating this gauge coupling at a high scale, due to the presence of superparticles, we realized that the 3-gauge coupling constant meets. Actually, here I quote this work done by Korean scientist, which was not really known at that time. So there were 3 different groups realizing this phenomena in a road paper, and then this paper was a bit behind, although it was written in the earlier than those papers, and somehow it has citation only 200. On the other hand, the other papers must have got more than 1,000 citations. Okay, so another impressive prediction of supersymmetry is that we have a neutral heavy particle like Higgsiano or Fortino, the superpartner of bosons, the fermion fields around TeV mass scale, which must have weakly interacting property. So this is a natural dark matter candidate as well. But I mean, so far there is no evidence. So up to TeV scale, about a couple of TeV, we didn't find any signal. It is not only for supersymmetric particles, also for other particles like extra gauge boson or extra quark and lepton families. So no new physics signal at all. So it was, I mean, so it's a nightmare theory scenario. It's really realized. Yeah, we can say so. Okay, now, we talked about Neutrino as a dark matter candidate. Actually, this story also starts with Benjamin Lee and Weinberg. Actually, at that time, it's 1977, actually neutrino, we didn't know whether neutrino is massless or massive. It could be massive. So if neutrino has a mass around 10 GeV, so they realized that, the weak interaction, it has only W boson and G boson exchange interaction, which is called the weak interaction. So having the property of weak interaction and a mass around 10 GeV, then actually it can give right amount of cold dark matter of the universe. So yeah, this is so-called WIMP miracle. Actually, since that time, I mean, we actually hoped for the realization of this so-called WIMP miracle. So actually, this WIMP miracle became more popular because the CMB measurement actually confirmed that the current universe must contain 20-30% of dark matter. So and then there are also a bunch of other evidences. If you look at the rotation curve of a galaxy, if you have any ordinary matter, then the rotational velocity can be much different from the observed one. So, so some in the galaxy, not only ordinary matter, there must be also unseen matter, so that we can have this observed rotational curve. Also for CMB anisotropy, we can, all the fluctuation of the CMB will generate, so the older matter will be fluctuating. So in some part is very dense and some sparse. So this will the main driving cause of matter fluctuation. So then at the end of the day, we'll be able to set up, form the galaxies and stars and so on and so forth. So if there is a dark matter and then dark matter first collapses, and then the local density can increase, and then later it can attract baryons, ordinary matter, in this dense area, so that we can correctly predict the the galaxy structures at present day. So that was one of the big success of CMB measurement. So that so this presence of cold dark matter is really very well confirmed by all different kind of experiment. So of course then, so we try to find this cold dark matter as a form of weakly interacting massive particle. If this neutrino is there, then it may collide with neutrons in the detector, and then it can give us some signal. But so far, again, no signal found. And then, there are a lot of neutrinos around us from the sun, atmosphere, so that so now current bound is getting deeper and deeper, so it can touch the actually neutrino background couldn't be seen. Somewhere neutrino background is somewhere here. So we are very close now neutrino background. So actually below the neutrino background, actually we will not be able to distinguish between the WIMP signal and neutrino signal. So now this WIMP scenario is also in danger. Okay, so but in the meantime, actually we have another good news from neutrino oscillation. So 1998, atmospheric neutrino oscillation was discovered. In 2002, solar neutrino oscillation was confirmed. So another neutrino oscillation from reactor was measured in 2012. So actually, for this discovery, the Korean experiment so-called Reno contributed together with China experiment called in Diabei. So this Super K and SNO, the atmospheric solar neutrino experiment, got Nobel Prize in 2015, and then this Diabei and Reno got some EPS prize a few years ago. So so let me just skip this neutrino oscillation story. Probably you heard about it many times. So this story is still going on. Previously to see this neutrino oscillation, another experimental setup, finally we identified two regions of oscillation parameter, and mixing angle and then mass squared. So atmospheric solar neutrino oscillation and atmospheric neutrino oscillation at these 2 points. And then now to make a more precise measurement, there are a lot of experiments still going on, having different neutrino traveling distance and then neutrino energy scale. So in the neutrino sector, we have 3 different masses for 3 neutrinos, electron, muon, tau type neutrinos, and 3 mixing angles, and then 1 CP phase, CKM-like phase. And then if neutrinos are Majorana, we have 2 more phases. So all the 6, 7, 9, 1, 2, 3, 4, 5, 6, 7, 9 parameters we should be able to determine in the future. So here is a very nice cartoon by Dent. So I mean, starting from 2000, 2022, I mean, you know, this is the precision of the measurement of each mixing angle, 2-3 mixing angle, and then atmospheric neutrino mass delta m squared, and then and so on and so forth. So now at the moment, I mean, this mixing angle measurement reaches about 1% or 1 to 10% precision. And then the least known parameter is the CKM phase. So still, I mean, it's not yet finalized. There is a slight favor for certain value, but there's still, I mean, we have to go on to determine more precisely. And then another 2 phases, for Majorana phases, we have no clue at all. So that has to be also determined in the future. So for neutrino oscillation experiment, I mean, we don't measure the neutrino mass directly. So we see only neutrino mass difference. So so from you know, the atmospheric neutrino mass difference says that delta m squared must be 10 to minus 3 electron volt squared, and solar oscillation is around 10 to minus 5 electron volt squared. Then you know, so we have 2 different type of mass ordering. So one is called the normal, and the other is called inverted. So normal, we say M3. The heaviest one is about 0.05 electron volt, explaining the atmospheric neutrino delta m squared. And then inverted, so 1 and 2 are almost degenerate, around 0.05 electron volt. So their splitting is very small to explain small atmosphere, solar neutrino delta m squared. So about 10 to minus 7 times 10 to minus 5 electron volt squared. But this difference explains atmospheric delta m squared around 10 to minus 3 electron volt squared. So these 2 possibilities still there. And then currently there is a slight preference to the normal hierarchy, but not yet at the level of discovery. Also, the CP phase, CKM CP, like a CP phase, it can be either pi, it can be close to pi over 2 or 3 pi over 2. But we have to, I mean, this has to be also decided in the future. And then concerning mass ordering, actually, the Juno, I mean, this is the bigger experiment than Diabe in China. Also, one of their goals is to determine this mass hierarchy. So by themselves, actually, they can reach the determinants of mass ordering at 3 sigma level about 7 years from now. But the interesting thing is that combined with all the other experiment, I mean, the long baseline experiment done in Japan or US, if we measure delta m squared more precisely at the level of 1%, then indeed we can reach 5 sigma discovery of mass ordering. So most probably, if this analysis is right, I mean, most probably in 7 years, we will determine, and one of the most important neutrino mass property, the ordering of the masses. And then to me, I mean, this is a more important property of neutrinos. So neutrino can be either Dirac or Majorana. So Majorana means, you know, neutrino can be antiparticle of itself. And then Dirac means that, you know, the neutrino and neutrino are different species, like electron and positron. So if this is Majorana, actually this can be a virtual particle emitting 2 electrons. So if it is Dirac particle, then we emit E minus, then on the other vortex we should emit E plus. So if neutrinos are Majorana, then the E minus double beta decay should occur. So now at the current stage, this is current limit for the double beta decay experiment. I mean, so for this to occur, I mean, actually the EE component of the neutron 3×3 neutron mass matrix has to be some sizable value. So current limit, I mean, this process is the amplitude is proportional to the mass of neutrino mass, EE component of neutrino mass. So the current bound for this quantity is about 0.345 electron volt. But in the future, maybe we can reach up to here, probably in 10, 20 years. So there is a lot of competition to see this neutronless double beta decay to confirm the Majorana perturber neutrinos. And then, of course, if neutrino masses are normal hierarchy, there are more parameter space which cannot be probed by this double beta decay experiment. So, I mean, to go down deeper, I mean, we needed to have some breakthrough in the technology. But the inverted ordering is right. I mean, perhaps in 20 years we may be able to see this event. Actually, inverted hierarchy is more interesting than normal hierarchy. So normal hierarchy is kind of boring, is as expected. So yeah, I really hope to have this inverted hierarchy or inverted ordering of neutrino mass. Okay, so CP violation. So we talked about neutrino sector. I mean, we now know that we don't know. I mean, but this can be a large number compared to the CP phase in the quark sector. So this has some relevance in baryon asymmetry of the universe. So to have, now we know that the current universe is composed only the baryons, not antibaryons. If you compare this number to the photon number at present time, is around 10 to minus 10. So there is very small fraction of baryon and antibaryon asymmetry. So in the beginning of the universe, we believe that the number of baryons and antibaryons are the same, but somehow there appears some asymmetry between number of baryons and antibaryons, or number of quarks and antiquarks. So just 1 in part of 10 to 10. So we have to arrange this small asymmetry. Then at the end of the day, this 10 to 10 quarks and antiquarks annihilate each other. So this appears, and then this 1 part of 10 to 10 remain to form all the atoms in the universe. So so this the matter-antimatter of the universe also is a mystery. So we should be able to explain why this can happen. Right? So this is another unsolved problem going beyond the standard model. And then of course, the neutrino mass in the standard model, neutrino is massless. But Weinberg himself also wrote down this dimension 5 operator of the standard model. So this is also standard model gauge invariant Lagrangian, lepton doublet, Higgs doublet. So this is also 4 field interaction. It has 2 fermions and 2 scalar field. This dimension 5 operator. So this operator is suppressed by 1 new physics scale lambda. So then after Higgs wave, I mean these 2 neutrinos can get mass like this, Higgs wave square divided by high scale, right? And then we know this value. So to get the neutron mass around 0.1 electron volt, maybe we should get some new physics scale around 10 to 15 GeV. So this scale is close to Gauss scale. So when neutrino oscillation was found, and then people thought that maybe this is indirect evidence for grand unification, but not necessarily. So it can come from some small couplings. So this single point, there may be some new physics mediating. I mean, we may have some heavy particle mediating this lepton and Higgs. Also, different kind of the fermions and scalars. Also, there may be loops inside, so that we can have small couplings through the loop correction. So this, of course, still we have many theories to get this effective Weinberg operator, but still we don't know which one is the right way to go. So this is one of those active research field in neutrino physics, together with experiment. Okay, so let me talk about my journey during this period. So as Sudhir introduced, actually for my PhD I did the superstring phenomenology. So around before 1980, actually, 10-dimensional string theory can have effectively the standard model, and then string theory should be able to explain why there must be SU3, SU2 cross U1, why there are three families, and so on and so forth. So at that time, how to compactification of 10-dimensional theory to 4-dimension should be able to reproduce standard model. So during PhD, I visited Munich under the joint project between Seoul National University and Technical University of Munich. And then actually, I was able to become a co-author of this paper. I didn't know why. So what I did was just learning this string compactification from them. So my contribution was almost, probably 2%. So anyway, I was one of the co-authors, so I learned a lot. But then after I get PhD, the string theory was kind of dead. So early 1980s, 1990s, actually there was no job for string theory. And then I had to move to phenomenology. So I start with Axino. Also supersymmetry. If there is a so-called action field, there must be superpartner called Axino. Then I worked under the Axino. And then when I was a postdoc in ICTP, the Anjan visited. So he had an idea that Axino may be a candidate of sterile neutrino. So we made a collaboration. So that's why my connection to India became so important. And then later, after super K discovery of neutrino mass oscillation, I worked on the alphabetic violation in supersymmetry to explain neutrino masses and mixing. And then Higgs discovery, after Higgs discovery, nothing was found. So supersymmetry became kind of that. And then I started to work on 2-HEDM, explain muon G-2. At that time, actually, Sudhir and my collaborator, Sudhir and Massimo Passera visited KIAS. So they had an idea what would happen for muon G-2 in 2-HEDM. So this was kind of one of the first paper I worked on non-supersymmetric theory. Okay, now remaining 6 minutes. I should finish my talk. So now some new development after the Higgs discovery I like to talk about. So now so far we kind of walk straight. So now it's time to take another route which we didn't explore. Actually, SNOMES 2021, they had a lot of discussions, and then so please visit this site to see a lot of new development in the field. So one of the direction, of course, is they have higher energy colliders. For instance, in Europe, so they are talking about this future collider, say 100 TeV machine extending LHC. Well, now United States, they rather go to muon collider, which was a kind of fashion about 10 years ago. Now they revived this idea. Then, okay, of course, one of the merit of muon collider is that actually this can reach around the 10 TeV energy scale. So probably there may be a chance to find the superparticle around, say, 10, just below 10 TeV. But still, I mean, after the death of SSC in US, their initiative in collider physics moved to Europe. Now, probably they try to recover their status on collider physics. So if they were able to set up a muon collider, maybe, but it's still, it's still R&D stage. So another direction I like to focus on is this direction, small couplings and lighter masses. So for this, you can start also good motivation. So in the standard model, we have another parameter, so-called the theta parameter. So this is also gauge singlet, gauge neutral. This gluon dual operator is also standard model singlet field. So this is a CP vibrating operator. In terms of electromagnetism, is like a E dot B combination of vibrating CP. So this CP, this theta parameter is CP vibrating parameter. So if there is such a parameter, one of the important consequences is that it can induce large neutron EDM. Actually, this Anson Hook have very nice cartoon explaining why theta parameter induce neutron EDM. Is this. So neutron consists of U quark, D quark, and D quark. They have different charges. If the three quarks display like this, then there is a disparity in the charge. So EDM is kind of charge times this separation of different charges, right? So pictorially, neutron EDM will be electric charge times theta parameter times the size of this displacement, which may be 1 Fermi. So this is maybe 10 to minus 13 centimeter times theta parameter, roughly speaking. But now current experiment says that the neutron EDM should be smaller than 10 to minus 26. So if you make some serious calculation, so we can see that theta parameter should be 10 to minus 10. So also like the small neutrino mass, so the theta parameter is also very small. So we may need some explanation why it is so small. So that was why so-called action was imagined. So if there is such a particle coupling to the glue-dual operator, it's a pseudo-Goldstone boson, and then F is the decay constant of the Goldstone boson. And then if this particle exists, actually it acts in this theta direction, so it pulls down this displacement to the zero angle. So what it does is that to make theta parameter to 0. So then we can naturally explain why theta should be 0 to explain the smallness of neutron EDM. So one of the prediction of this is that the action mass, actually after QCD condensate, action mass is determined by the QCD condensation scale squared divided by its decay constant. So it's very, very light particle. So actually, this band in terms of the mass and then decay constant. So this is a QCD window. So now the QCD action mass should be, there is an upper limit from the the neutron star or supernova cooling. So the mass should be below a milli electron volt, but must be larger than around 10 to minus 6 micro electron volt. So if the axion mass is lighter than 10 to minus 6 eV, then I mean the axion itself is a cold dark matter candidate. So it is known that in the standard scenario, axion mass lighter than 10 to 6 GeV overproduce dark matter density. So there is a rather tight axion window of the mass between milli electron volt to micro electron volt, corresponding to the decay constant from 10 to 12 GeV to 10 to 10 GeV. So this is axion window. So there are a bunch of experiments to try to see this dark matter axion. And then, of course, well, in some cases it can extend to lighter masses. And then now people are thinking of maybe not only axion, there may be some light pseudoscalar having axion-like property, which is called axion-like particle ARP in short. So now people are trying to see some exotic event of the light particles inventing a lot of different kind of experiment. So now the proposal, there are novel proposals to detect light particles, so that I mean this is really impressive proposal. I mean we may be able to find some new signal down to 10 to minus 10 electron volt and so on and so forth. Okay, so now because of this, people are thinking of huge territory of dark matter mass. So down to 10 to minus 20 electron volt to up to Planck scale, even 10 solar mass, black hole. There may be some primary black hole produced after inflation. So this also can be a dark matter candidate. Some black hole mass range. I mean, this dark matter can be 100% of. It can from 100% of cold dark matter. Also, lighter side, I mean, if you have light particles, it behaves like a wave. It's like a classical wave. So actually, QCD axion was the first example. So then we can extend it to be any other light particles. So then 20 years ago, these people realized that actually if there is a light particle, it can be a classical wave like. And then if this mass is around 10 to minus 2 electron volt, their double length is around 1 parsec. So that means, this wave, this large wavelength particle is present. We are living in this wave, so it has certain pressure to erase smaller scales. So scales smaller than around 1 parsec cannot develop. So this is the outcome of calculation. So 10 to minus 20 electron volt mass particle can, this is a fluctuation. So usual cold dark matter can produce larger fluctuation up to some megaparsec, but fuzzy dark matter, wave-like dark matter, so below certain parsec scale, smaller scales cannot develop. So in this way, it can have also very important cosmological astrophysical implication. And then since then, actually, people try to see this impact. Actually, during past 10 years, we realized that considering different type of experiments, observations, actually we can rule out large part of the parameter space. So we are basically now the first dark matter mass below 10 to minus 18 GeV is basically ruled out, and there is a small window around 10 to minus 11 GeV. Also below 10 to minus 10 to minus say 10 GeV, so it's disfavored. And then now people are trying to cover this parameter range then inventing some new way of detecting these particles. So, yeah, let me just tell you one of my work in this direction. So, if there is such a light particles, wave-like particles around 10 to minus 10 electron volt, so there could be huge medium effect. You know, so around us we know the dark matter local density, which is about 0.3 GeV per cubic centimeters. Then if this is classical wave, its amplitude is determined by this quantity. So if we have 10 to minus 22 electron volt dark matter, then this amplitude is 10 to 10 GeV. It's a huge amplitude. So if this guy couples to standard particles, for instance, neutrinos, so you can give large masses to neutrinos, so that we have to suppress this coupling below the certain value, right? So neutrino mass is known to be around electron volt. So that, and then, so this coupling should be very small. So you can make it small. And then if this coupling is flavor dependent, actually this can induce neutrino oscillation. So even for massless neutrinos, even tree level mass is vanishing due to this matter effect. We can have neutrino oscillation effect. So, I mean, this is kind of crazy idea, but there is such a possibility. So, so we wrote this paper. Actually, this idea was declared by Wolfenstein himself, who realized that in the solar medium there is a matter effect. Solar neutrino can get Wolfenstein potential. So of course, in the standard model, the weak interaction cannot give this kind of mass term. It can produce only the potential term, which is of course important for solar neutrino oscillation. But then he also discussed that if there's a flavor-dependent neutrino medium effect, it may be the source of neutrino oscillation, but not applicable to the solar medium. So actually, we are really discussing this kind of effect in terms of dark medium. So yeah, in homage to his paper, yeah, so we can kind of consider the neutrino oscillation in dark matter in this way. Okay, so time's up. Maybe I better finish. So let me skip the baryogenesis idea, and then my recent work on this probably. So let me just finish by quoting Albert Einstein, like this. Okay, thank you very much. Slide 29. Okay. Okay, this one is from PMNS. It's yeah, Dirac phase. We don't know yet. So I can hear. Could you speak up? Could you speak up? Yes, yeah, it seems. I mean, you know, currently pi over 2 is preferred. So then it's a kind of a maximal. But we don't know. I mean, okay, so there could be large CP violation, but not yet clear whether it will be the source of a CP violation for baryogenesis. Yeah, there are models like that, but there may be other models. So yeah, I mean, so large CP violation in neutrino oscillation is not directly related to the baryogenesis. but it could be a good starting point. So it can be used for baryogenesis in seesaw model, neutron mass models. Mm-hmm. Yeah, that's a good question. Still, it feels like a mass. Okay. There is a tricky point. I mean, okay, if there is such a mass in the early universe, of course, yeah, I mean, they also behaves like a ordinary tree-level mass. So there is no distinction. But the one thing I didn't talk is that, if this is really from dark matter density, back at the CMB time, the dark matter density is much, much higher. So the corresponding classical amplitude is much larger. So by the same coupling, the mass can be much larger than the temperature at the time. So, so in the standard cosmology, this scenario is that. So then, I mean, so we need distort our scenario. So there was a question, yeah. Sorry, could you? Okay. Uh, 10 to minus maybe 10 to minus 5. Minus 6, yeah. Okay, so yeah, actually, I think this is not current bound. It's a future possibility. And then, okay, so probably I think I cannot answer you this properly. So I'm not expert in this field. So yeah, please go to this reference to know more in more details. Mm-hmm. Yeah. No, no, no. If you have any new particles, then it goes away. Yeah, any kind can do. Of course, there's some range of parameters which can remove this vacuum instability. But, I mean, it's more or less straightforward. So if you have any scalar coupling to the Higgs, vacuum stability can be satisfied easily. Okay, thank you very much.